Hello, everyone. Today we're going to go over Chapter 3, the chemistry of organic molecules. Last chapter, we ended with the chemistry of atoms, their subatomic particles, and how they make up compounds and molecules. We're moving larger and larger. Our scale is, moving backwards, and we're getting larger and larger and looking at different molecules at that specific scale. Today we're going to be looking at Chapter 3's macromolecules, which are, there's 4 different macromolecules: lipids, proteins, nucleic acids, and carbohydrates. We're going to look at their properties, how they're built, how they're broken down, and just different characteristics of each. But first, we're going to talk about organic molecules. Organic molecules is just a vocab word that you need to know going forward. You might have heard organic chemistry. Organic chemistry and organic molecules deal with any molecule that contains carbon and hydrogen. We more typically, identify these molecules with a carbon, just because hydrogen's in most molecules, just because it's a good filler molecule, or I should say, element. These organic molecules also contain oxygen, nitrogen, phosphorus, and or sulfur, and in a combination. We're going to talk about what elements are found in which macromolecule. So some macromolecules will have all of them, some macromolecules will only have a couple, but as long as they have carbon and hydrogen, we know them as organic molecules. So why are we focusing on carbon? Carbon has 4 electrons. If you remember the valence electrons we talked about last chapter, carbon has 4 of those valence electrons in its outermost shell. Now, it has 6 total electrons, but the 2 first electrons are within the first orbital, and they're happy being bonded by themselves. The 4 valence electrons in the next outer shell are the valence electrons, and they're going to be able to bond with 4 other elements, are actually forming covalent bonds. Remember, those covalent bonds are very, very strong, and they connect to either carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, or any really other molecule, or I should say element, within the periodic table that can bond with carbon. Carbon is a very versatile element because it can bond those 4 different elements, or 4 different locations. When we see these carbon atoms bonding with, let me go back. When we see these carbon atoms bonding and forming almost like a line, we call this a carbon skeleton. You can see these are all hexane molecules right up here. You can see the carbon here all bonding to themselves, or hydrogen, and then you can see how it is different in these different structures below. All for the first 3 of these are hexane. You can see how, again, carbon has 4 different locations where it bonds with different elements. This middle carbon here is bonding with the 2 side carbons and 2 hydrogens. This end carbon here is bonding with 3 hydrogens and 1 carbon. That's why, again, carbon is so versatile. It just bonds with a lot of different elements and has 4 locations where it can bond. Again, these are all organic molecules. Even though they don't have oxygen, phosphorus, and all those other elements, as long as it has carbon and hydrogen, we know it as organic. Here's some more examples of carbon structures or organic structures. And you can see there's specific ways to name these. You can see ethane, propane, 1-butene, 2-butene. We're not going to go over the naming. That's called organic chemistry, and that is a tough class you're going to see in college. You can see all of these have a carbon skeleton to them, and they're highlighted in green. I'm just showing you more examples of that carbon skeleton from the last slide. Now, moving on, functional groups. This is another important aspect of macromolecules and biochemistry. Functional groups are specific combinations of elements bonded together that we see quite often in chemistry and in biology. You can see here are some of the examples in the functional group chart. You see hydroxyl, OH. Remember the hydroxyl ions from last chapter? This is just a functional group, which means it's attached to a larger molecule. Whenever you see this R group, that's just telling you there is a whole nother structure here. It could be just one carbon atom. It could be, a whole molecule of glucose or something else. All we're looking at is this functional group of OH. The carboxylic acid, COOH, that's another typical functional group that you're going to see in biology, especially within carbohydrates. Again, the R's are just letting you know there's other elements there, but when we see like this combination, they all have specific names. Great part about the functional groups, you don't have to memorize any of them. You might, I would recommend you knowing carboxylic acid and hydroxyl, just because we will see those quite often, but the AP biology test is going to say, hey, what group is this? That's memorization that's outside the scope of AP biology. Next, we have isomers. Isomers are when organic molecules have identical molecular formulas, but their structural formulas are different. What that means, molecular formula is down here at the bottom where it says C2H6O. That means that is a molecular formula is going to be the same for different isomers. You can see here dimethyl ether and ethanol. They have the same molecular formula, which means again C2H6O, C2H6O. These here are the same. However, their structural formulas are different. If you look here, it's you have a CH3 group, a CH3 group, and an oxygen group. Now or if we go back to the functional groups, we could identify some of these functional groups in these two different uh, molecules. Like over here is a hydroxyl group, but we don't need to know that just yet. Isomers are just when they have the same molecular formula but different structural formulas. You might not think like, okay, they're just put in different ways. I'm going to tell you something here that you're going to use the rest of the year. And if I had my AP biology class here last year, they'd be rolling their eyes because they would say, learn this now. When you change the structure of something, you change the function. So even though these have the same elements, the structure will dictate the function. These two will not react the same way. These are like brothers and sisters, kind of like a family. They maybe look the same, maybe they have a lot of characteristics, but they are functionally different. They will react different. When you put ethanol on something versus dimethyl ether, it will react differently. Even though it's made up of the same things, again, C2H6O, C2H6O, it will react differently. Next part of this chapter is going to talk about how macromolecules are formed and how they're broken down. There's two different types of reactions. The first reaction is a dehydration synthesis reaction, and the next reaction is a hydrolysis reaction. Let's talk about dehydration synthesis. If you hear the word dehydration synthesis, think in your mind, what do you think of automatically? The first thing you think of is that second word, synthesis. What does synthesize mean? Synthesize means to produce or to make. So in dehydration synthesis reactions, we're actually going to make something. We're going to grow. It's going to grow. It's going to become bigger. I know it might sound like, like the words don't match. Dehydration, you're taking something away, but you're building something up. How can that happen? So whenever a dehydration synthesis reaction occurs, when you're dehydrated, you're taking water away. So think about this reaction when you're dehydrated. You take water away from your body. Maybe you were outside too long and you sweated too much. What you're going to actually do is you're going to form water by taking a hydrogen and a hydroxyl group away. If you can see, when you add these two together, you're going to form water. When you form that water, you're taking it away from the reaction. Now, what we're actually doing here is we're taking monomers and we're building up a polymer. Now, like I described in the previous chapters, what does mono mean? Mono means one. What does poly mean? Poly means many. So we're taking a bunch of monomers and we're making a polymer. I describe this as whenever we're talking about monomers, think of bricks in a wall. The bricks are the monomers. The whole wall itself is the polymer. There are many bricks, which are monomers, but there's only one large polymer, which is made out of monomers. Now, to show you what this reaction looks like, again, you can see here the two monomers and their hydroxyl and hydrogen groups. What's going to happen is there's going to be a reaction where these two come together and they're going to form water. And these two monomers are going to bond together and form this covalent bond. This here is a polymer because it's many monomers. Our next reaction is a hydrolysis reaction. Again, break down these words. What does hydro mean? Hydro means water or something pertaining to water. Lysis. You might not understand that or realize what that means. It means to break down. So we're using water to break something down. This reaction breaks down polymers, again, poly meaning many, into monomers, meaning one. This is just the reverse reaction of dehydration synthesis. So think what happened in dehydration synthesis. We took out water and we put monomers together to form a polymer. This is the reverse reaction. You're taking a polymer, you're adding water in, and you're going to break these monomers up. So you can see here it says water is added, which splits into H and OH and detaches the monomers between the polymer. Let me show you what this reaction looks like. Again, we're taking this polymer here, we're adding in water. Now that water is going to split and you're going to get a hydroxyl and a hydrogen group. These monomers then have been split through this hydrolysis reaction. Our last slide for this chapter. Our last slide for this chapter is on the 4 different macromolecules. Big hint here, I would just memorize these things. There are some things in biology where you just have to memorize just to know them going forward. This is one of them. So you have 4 different macromolecules. You have carbohydrates, lipids, proteins, and nucleic acids. You need to know their monomers and their polymers. For carbohydrates, it's pretty easy. Monosaccharides and polysaccharides. So monosaccharides is the monomer, polysaccharides are the polymers. Very easy. For lipids, it gets a little confusing. You can have glycerol and fatty acids as the monomers, and the polymer is a fat. Now, there are other ones. Lipids is just that one that doesn't play by all the rules. We'll talk about that later on. Proteins, the monomer are amino acids. They are monomers. A polymer is a protein, or it's called a polypeptide. Lastly, nucleic acids. The monomer is a nucleotide, and polymers are DNA and RNA. We're going to spend a lot of time talking about carbohydrates, lipids, and proteins in this chapter. We mentioned and we do go over nucleic acids, but we wait until later on in the year to nucleic acids because it's a whole unit that we spend on nucleic acids.